In this lecture, we're going to see how to plot 2D arrays, error bars, histograms, and how to create composite plots. We want to visualize this equation of two variables. First, we create a row and a column vector of evenly spaced integers between -1000 and 1000. Second, we create a 2D NumPy array by adding the row vector squared to the column vector squared. Using Boolean masking, we equate to 0 the values outside the circle of radius 1000, while the ones inside are set to x times y. We plot this 2D array as an image using the impShow function. We pass the array to the function and specify the location of the lower left and upper right corners, as well as the color map. Here we choose the sequential Viridis color map. We also plot the color bar and assign labels for x, y, and z. We use both TeX expressions and Unicode characters. TeX expressions have to be enclosed in a pair of $signs. When we use backslashes, we precede the string with the letter R to indicate that the backslash is not to be interpreted as an escape character. If we look carefully at the plot, we notice that the regions inside the circle where x and y have the same sign have negative z values, as shown by the blue color. This makes us realize that something is not right with the plot. It turns out that, by default, impShow places the origin of the 2D array in the upper left corner. Instead, we want the origin to be in the lower left corner, which is easily achieved by specifying origin equal to lower. The reason for the counterintuitive location of the origin is that raster images, which are arrays of RGB values, have the origin in the upper left corner. To show that, we read a PNG into an array. We plot the array with impShow, setting origin to upper, and we see the expected image. If we instead set origin to lower, we obtain the mirror image. Now let's get back to the Eurostat dataset on waste generation. We select a cross-section of the multi-index data frame which we created in a previous lecture to obtain the total amount in kilograms per capita of non-hazardous plastic waste for all EU countries in the various years. The describe function of the data frame conveniently returns statistics summarizing each column. For each year, we obtain the number of values, the average over the countries, the standard deviation, the minimum, the lower percentile, the median, the upper percentile, and the maximum. We now want to plot the average amount of plastic waste over the 28 EU countries versus the year, showing the error bars. We create 3 NumPy arrays for the years, the averages, and the standard deviations. These are passed as the first 3 arguments of the error bar function. This function can also plot horizontal error bars for the uncertainties on the x values, as well as asymmetric error bars. Here we also customize the width of the error bar, the length and the thickness of the error bar caps. How is the distribution of the amounts of plastic waste generated in a given year? To visualize that, we first compute the histogram of a column of the plastic data frame using the NumPy histogram function. We specify the edges of the bins, including the rightmost extremity, as a NumPy array of integers from 0 to 60 with a spacing of 10. The histogram function returns 2 arrays, the values of the histogram and the edges of the bins. Since we want each histogram value to be centered on the bin, we create a new bin array which excludes the rightmost extremity and is shifted by half the bin width. We create a bar plot from the histogram values versus the new bins using the pyplotbar function. We set the parameters width to the bin width and edge color to black to define the contour of the bars. Pyplot provides the hist function, which allows you to create the exact same plot in a single line, passing only 3 parameters. In scientific publications, several plots are often combined in a single figure. Here we will see how to create 3 types of composite plots: plots with 2 y-axes, composite plots on a regular grid, and composite plots with subplots of different sizes. When we want to plot in the same graph 2 datasets with y values on very different scales or representing different quantities, it is desirable to assign the y-axis on the left-hand side to one dataset and the y-axis on the right-hand side to the other. To do that, we create the figure and axis objects, and we plot the first dataset on this axis. Here we are plotting the plastic waste generated in Greece through the years. Then we create a twin axis with the x-axis in common, and we plot in it the second dataset, in this case the glass waste generated in Greece. All that is left to do is to label the axis and to color the y-ticks and labels to match the color of the corresponding lines and markers. To create composite plots on a regular grid, we use the subplot function. This function takes as arguments the number of rows and columns of the desired grid. We can further specify the size of the figure and if we want the x and y axis to be common to all subplots. The function returns the figure object and the array of axis objects. The array has as many rows and columns as the grid. In this case, the array is unidimensional. We want to plot the plastic, glass, and paper and cardboard waste generated in Greece. We create a list of strings for the names of the different materials. We loop over the array using enumerate. This built-in Python function allows us to automatically get a counter together with the entries of the array. We use the counter I to index the list of materials. We label the y-axis of the outer subplots, and we place the label and ticks of the rightmost subplot on the right-hand side. For the middle subplot, we specify that we want y ticks on both sides. Instead of enumerate, we could have used zip, which is another built-in Python function to simultaneously loop over multiple iterables. In this example, we create a 2x2 grid and obtain a 2x2 array of axis objects. We unpack it into tuples corresponding to the 2 rows. When we use zip to loop over the axis of the materials, we have to flatten the axis array to make it unidimensional. To create a composite plot with subplots of different size, we use the function subplot to grid. The first 2 arguments are tuples. The first tuple is the number of rows and columns in the grid, whereas the second tuple is the coordinate of the upper left corner of the subplot axis in terms of row and column. The rows are numbered from top to bottom, whereas the columns from left to right. We need to specify the number of rows and columns that we want the subplot to span. Here we want a grid of 2 rows and 8 columns. The first axis that we create is located at the origin and spans 2 rows and 4 columns. In this larger plot, we plot the plastic waste of 8 countries versus the year. Then we use a for loop to populate 8 smaller subplots distributed in 2 rows on the right-hand side of the figure. We use the counter provided by enumerate to keep track of the row and column number. When plotting categorical data, the x-axis labels are often long strings. To make space for them, we tilt them using the parameter rotate of the xTix function. With MATPLOTLIB, we can render and save figures in a large number of formats, from vector graphics like PDF and EPS to raster graphics like PNG and JPEG. Here we save this composite plot as a PNG with 300 dpi resolution. When we read and plot the raster image with imshow, we notice that the lower part of the figure has been clipped. To adjust the location of the subplots so that all parts of the plot fit into the figure area, we use the tight layout function. This function also allows us to customize the vertical and horizontal distances between subplots, as well as the padding from the border of the figure. The format of the figure is deduced from the extension of the file name. Here we save the same figure in PNG, JPEG, PDF, EPS, and SVG format.